So we've looked at the first example for the Born-Haber cycle. So we've looked at how you construct the Born-Haber cycle for sodium chloride and how we manipulate the numbers on the cycle to work out the last enthalpy for sodium chloride. So now what we turn our attention to is seeing how the Born-Haber cycle might be slightly different for different types of ionic compound. Now before you panic, the cycle is not massively different, it's more or less the same and will look visually kind of similar. But there are a couple of wee differences you need to be aware of because again, in the exam they could ask you to do the Born-Haber cycle for a number of different ionic compounds. So you need to be aware about what the differences might be between them. Being a bit more specific, the bit that actually could be different, again I said most of it is the same. This kind of region of the Born-Haber cycle where you have the last enthalpy in the bottom right and then the bottom changes the enthalpy of formation, that will kind of stay the same. The bit that will actually be different is kind of all the working out for all the wee steps you do to finish off your cycle. So this region here might be different depending on whatever compound you're using. In terms of what I mean by different types of ionic compound, because you might think surely all ionic compounds are this kind of the same, you are basically correct. It's to do with kind of their charges and in terms of how the formulas look, it might affect the cycle you have to actually draw. These are actually the 4 different combinations which CSA can come up in your exam. Group 1, Group 7 ionic compounds, Group 2, Group 7, Group 1, Group 6 and Group 2, Group 6. Will make a bit more sense when we actually look at some examples. The Group 1, Group 7 one is the one we've actually looked at already. Sodium is in Group 1 and chlorine is in Group 7. So the bit I'm going to hone in on is where we're going from the elements all the way to the end of the cycle where we're trying to get the 2 separate ions as gases. So I'm going from this step to this step. That's the bit that can be different depending on what ionic compound you're looking at. So just by looking at the simple first case, what we were trying to work out was the number of different steps we use to go to sodium ion as a gas and a single chloride ion as a gas. So all different steps involved using the atomization of sodium, the first ionization energy of sodium, the atomization of chlorine, and the first electron affinity of chlorine. So there's 4 steps we had to do that conversion. For a Group 2, Group 7 compound, we might be looking at something like, let's go for MgCl2, magnesium in Group 2, chlorine still in Group 7. So the change I'm looking for here is Mg is still a solid. Now I have to be careful here. In my lattice enthalpy, I'm talking about splitting apart 1 mole of lattice, which is MgCl2. That means I'll actually form 2 chloride ions in this case. So I actually need to use a full chlorine molecule to get 2 chloride ions when I break it apart. So that's one wee difference. So it's going to break apart to Mg2 plus as a gas and 2 chloride ions as a gas. So already we're kind of seeing a couple of different changes here. I'm still going to have to do an atomization for magnesium, but I'm going to need to do 2 ionization energies because it's going from neutral to 2 plus. With chlorine, as I mentioned, because it's MgCl2 rather than just NaCl, I need double the amount of chlorides or chlorines in my equations. So I need to start with Cl2. That's going to change that value. Though the charge at the end is still Cl minus, so that won't be changing the electron affinity. So a couple of changes just at the start. The other variations we can have, let's look at Group 1, Group 6, that'll be something like Na2O. So again, we've got 2 sodiums here. So I'm going to have 2 Na at the start. I've only got 1 oxygen, so I'm going to go back to using like a half O2 to make 1 oxygen at the end. And at the end of the cycle, it's going to end up being 2 Na plus as a gas and an oxide 2 minus. So in this case, I have twice as much sodium as I do in the first example. It's only going to 1 plus though, so that's just 1 ionization energy. I've only got 1 oxygen, so that's just the atomization energy of oxygen, but I have to add 2 electrons to it to get to be 2 minus. And the final example you have to look at is Group 2, Group 6, which is MgO is a good example of that. Now there's only 1 of each, makes it a little bit more simple. So Mg plus a half O2 going to Mg2 plus. Sorry, I should put state symbols in here. Mg2 plus as a gas and the oxide ion as a gas. So there's nothing tricky about the numbers here, but again you see the charges are different. I'm going to have to use 2 ionization energy to get Mg2 plus and 2 electron affinities to get the oxide 2 minus ion. Don't worry if you haven't followed every word of that, like that's just me going through quite quickly, but hopefully you appreciate the fact that the exact changes you undergo in working out your last enthalpy will be affected by kind of the charges of the ions and how many ions you've got there. It's not going to be identical in each and every case, as we'll soon look at. So what I've just kind of gone through there is kind of alluded to at the bottom of this page 4. It just talks about how the Born-Haber cycle isn't identical for every ionic compound. It looks quickly here at the example of magnesium chloride, where your magnesium needs 2 ionization energies, and in fact you've got 2 chlorine atoms instead of 1 in NaCl. So that's just what we talked about. What you'll find on the next page maybe looks a wee bit overwhelming. These are actually the examples of the 4 different types of Born-Haber cycle you could potentially be asked to draw in the exam. Now, it probably does look a wee bit overwhelming. Just to make it clear at the start, I'm not suggesting in any way that this is something you should be rote learning off, all these different diagrams. This definitely is one of the things in chemistry that is easier actually if you know how to do it from scratch. That's quite hard to actually just learn off by rote learning, but the steps aren't that hard to follow. Now, I could go through and show you how each and every one of these is constructed, but that'll make quite a long video. I'm going to show one variation, probably the MgCl2 one, and I'll maybe just mention the points that are different about the final 2. The top left one, just for comparison, that is the one you've already got in your notes. That's the one we've looked at. This is NaCl. It's a group 1, group 7 compound. We're going from NaCl to Na plus Cl minus. And we go through all the changes we've gone through before. Atomization of sodium, first ionization energy of sodium, atomization energy of chlorine, and then the first electron affinity of chlorine, and that gets us to the point we need to for our cycle. So the one I said I go through in a little bit more detail just to show you the difference is MgCl2. So I'll show you how to do this one from scratch, which you could potentially have to do in an exam, and I'll hopefully give you an idea of how you maybe approach a more unusual one that could come up. So we'll come back to this. It's given to you as an example, but we'll show you how to do it from scratch here. So the key step for forming any Born-Haber cycle is knowing what you're aiming for, so knowing your start point and your end point. The bit I always think is best to start with is just your ionic solid at the bottom. So in this case we're looking at MgCl2 as a solid. The energy we're trying to work out in every one of these examples is generally going to be the lattice enthalpy, which is the energy to break that ionic glass apart to go to separate ions in the gaseous state. And again, you have to be really careful here, think about what you're going to form. Magnesium is group 2 ions, it must go to Mg2+ whenever you split up the ions in the lattice. Be really careful again because it's Cl2 to make the swap and drop for the formula work, therefore I have to keep those 2 chloride ions at the end there, so I have to pay attention to that. So that's my last enthalpy I potentially having to calculate here. And then trying to get through the rest of my steps to work out what that last enthalpy might be. Generally, the first arrow you put is the enthalpy of formation, because that's linking this all to your elements in their standard states. So that's generally going down, again, depends on what the actual formation value is. That's going from the elements in the standard states, just have to make sure all balance is out. There's going to be 1 magnesium atom, and then I'm going to use a chlorine molecule, and a full one because I need 2 chlorides in the ionic lattice. So that's the general format for every cycle at the start. The salt at the bottom, the 2 ions split up on the top right for your last enthalpy, and generally the one you put above is the formation enthalpy here from the elements. And this is where you kind of have to use your bit of logic thinking to work out the rest of the cycle. So take 1 ion at a time and work out how you need to change it to get from here to here. So always compare these 2 points to work out what you need to change. Let's look at magnesium first. The first thing that's probably easiest to change is the state. So you need to turn it from solid into a gas. So that's known as the atomization energy of magnesium. So you need to convert it into a gas. I'll keep the chlorine just exactly the same. And that change there will be the atomization energy to turn it into single atoms for magnesium. Once I've got there, I need to convert it the charge. So this involves 2 steps in this case. It's going from magnesium to magnesium 2+. That's not one individual step. It's actually 2 separate ionization energies. So I should draw both as separate steps here. So we're going to go to Mg+ as a gas and draw the electron alongside it. And then need to do it a second time to get the 2+ charge. So now I've got 2 spare electrons at the end. Maybe I haven't given myself enough room here, but the first arrow is going to be my first ionization energy, and the second arrow is going to be the second ionization energy, i.e. 2. So at this point my magnesium is all set up. It looks identical to how it looks at the other side of the cycle, so it's now completely done. My next step is actually working out how to get the chlorine to look like the chlorine does on the right hand side. First thing you need to do is split it up into individual ions. So that's going to be to do with the atomization energy of chlorine. So if I think about what I have to aim for here, magnesium is all done and dusted. So I need to end up having 2 single chlorine atoms there by splitting up this chlorine molecule with the 2 electrons still there. So I'd say from experience, this is probably the step where people get most mistakes on with your diatomic element, because it could be 2 potentially different energy values they give you in the question. In other words, they could give you atomization energy or the bond dissociation energy. If you think about what change I'm actually doing here, Cl2 is going to 2Cl. That's breaking apart 1 mole of bonds to make 2 moles of atoms. So in the question, they might give me the atomization energy of chlorine. This is where your definitions come in handy. Remember, atomization energy is the energy you get when or energy you need to make 1 mole of atoms. I'm making 2 moles of atoms here. So if they did give me atomization energy, I would have to double it. However, in this case, if they gave me bond dissociation enthalpy, that's breaking apart 1 mole of bonds, which is what I have in 1 mole of Cl2, to make 2 moles of atoms. So for this step, again, it just depends on the question. They'll probably try and trick you. If they give you the bond dissociation enthalpy, that is the correct value for this. But they could potentially give you the atomization energy, which you'd have to double. So that's our chlorine almost taken care of. The last step is I need to get to Cl-. So I've got 2 chlorines to turn into 2 Cl-. I therefore would need 2 moles of electrons to do that. Luckily I've got that from my magnesium steps, so I'm going to convert this down. And again, this is the last step you can maybe trip up on. They might just give you the electron affinity for chlorine. That's the correct value, but I need twice that value because I've got 2 chlorines undergoing that change. So what I put in this arrow is 2 times the electron affinity for chlorine. And hopefully, if I've done this correct, this should look exactly what I've got on the printed version. So you see that atomization energy of magnesium, first and second ionization energy. You've got this variation where you might have the bond dissociation enthalpy or double the atomization energy for chlorine. And I have to use twice the electron affinity for chlorine because I've got 2 of them here and 2 of them here, and that's the cycle. And again, once I've done that hard work, the maths should be straightforward enough. It's just going to be putting numbers on these arrows and manipulating the cycle. This is always a tricky step for what you have to work out in a question. So that's a group 2, group 7 example. We'll look quickly at the other 2 examples. Again, the same kind of thought process here. I'll not do it all, but just kind of point out the differences. With Na2O, what we kind of talked about is the fact that if I'm splitting up from Na as a solid and a half O2, I'm going to need 2 NAs because there's 2 in the formula, and it's going to give me 2 Na plus ions at the end and an oxide ion at the end. So again, the service cycle is the same. I put my salt at the bottom, I put my split up ions at the top, and I put the elements above on the left hand side for the formation. So if you follow the cycle round, the first 2 steps are kind of straightforward. You atomize your sodium first, turn it into gas, and then you ionize it once to turn it into sodium plus. What you should notice though is because there's 2 sodiums in this cycle, because there's 2 in the formula, I'm going to need to double those values from the table when I do my calculation. With the oxygen, it's straightforward enough at the start. I've got half mole of it. I'm going to be forming 1 mole of oxygen atoms. That's the atomization energy of oxygen. Or if they do give me bond dissociation, I'll just have to half it because I've got half a mole of oxygen bonds. This bit looks a bit different here. Remember, I have to form an oxide 2- ion. The first electron affinity is just as expected. It goes exothermic, so it gets rid of 1 electron. There's actually a wee typo here. That should just be O-. Now the difference here is adding the second electron. What we looked at in the first page is that the second electron affinity is actually always endothermic. Doesn't really matter that much, just means the arrow has to go up to finish off the cycle. So again, it looks a bit different. It's just adapting your steps to get from here to here in a number of steps. Now the final example, group 2, group 6, so MgO will look like this. So I need an Mg and a half O2. I'm going to go to the Mg2 plus ion and the O2 minus ion. And that's from going from this step to this step. So starting my cycle as normal, put the salt at the bottom, put the still ions on the right hand side with my last enthalpy. Above the ionic glass on the left hand side, I put the elements in their standard state, put the enthalpy of formation there. That's always the same. Then I come to these steps to work out the other side of the cycle. So looking at magnesium first, need to atomize it first. That's just straightforward enough. Need to do 2 ionization energies to get it to be Mg2+, we've looked at that before. Then we look at the oxygen. Again, there's half a mole of it, so that's going to be the atomization energy to make 1 mole of oxygens. And then because I'm forming O2 mass, I need to do 2 electron affinities. First one's exothermic, second one's endothermic, and that gives me my cycle. So hopefully you followed those 4 different kind of variations of the 4 cycles you can get. It might be a case of you taking a step away from the video with a blank bit of paper and seeing if you can do these from scratch. I promise you will be able to get them. They do look a bit overwhelming at the start, but just follow the same format. Start with your salt at the bottom, your ions separated on the right hand side, and just see if you can work out the steps you take to get along the left hand side, and just check back to here to make sure you've done it correctly. Once you think you're happy with them, on the next page there's a wee kind of chance for you to see if you can do the calculations with them. So I've given you the cycles for MgCl2, Na2O and MgO. What you'll find here is the relevant data tables to work out the last enthalpy for those. So what I suggest you do, having looked at the first one, it's not any different. You just put the arrows on the numbers on the arrows and just check back. Well, I'll go through the working out for those answers here. So the first question looks at MgCl2, which is top right on page 5. And again, gives you all the numbers you need, just need to transfer them across and be careful that you're multiplying by what you need to multiply by. So the first one is formation, so I've taken the liberty of flipping that already, so it's now plus 642 because I need to flip it to get around the cycle. The first few are all just straight off the table. Atomization of magnesium plus 150, first ionization energy plus 736, and then plus 1450 for the second one. Again, this one I always have to double check. What they gave me in the table was the bond association enthalpy of chlorine. And if I look, that is actually the change that we're undergoing here. 1 mole of bonds of chlorine is giving me 2 moles of atoms of chlorine. That is just the bond association enthalpy, so just keep it the same. Last wee bit I can get tricked out on, with the electron affinity, it's given as minus 364. However, I've got 2 chlorines forming 2 chloride ions, so I need to double that value to get it correct. Once I've done that, it's just a case of typing it on the calculator. Plus 642, plus 150, plus 736, plus 1450, plus 242, plus 2 times minus 364 should come out in your calculator as being plus 2492 kilojoules per mole. Second example is sodium oxide. So again, these are the values given to you. So formation sodium oxide flipped to make it plus 416. For these first 2 changes, I need to double them because I've got 2 sodiums in my cycle. So therefore, it's twice the ionization energy and twice the first ionization energy. Again, being careful with my oxygen here. The change I've got in my cycle is it's half a mole of oxygen going to 1 mole of oxygen atoms. So that's just the atomization energy of oxygen. However, as you see in this table, they give you the bond association enthalpy of oxygen, which would be breaking 1 mole of bonds. So in other words, that value is double what I need it to be, because that would be to form 2 oxygen atoms. Therefore I need to half it. So half times plus 496. The remaining 2 steps are just straightforward enough because only 1 oxygen. Doing first electron affinity minus 142, second electron affinity plus 844, and those are my values I need for that cycle. Typing those all in my calculator, just adding them all together, should come out as being plus 2582 kilojoules per mole. Final example is MgO. So it's actually simpler because you actually need to multiply anything up in terms of having 2. It's just 1 magnesium and 1 oxide at the end. So 602 flipped goes to plus 602 for the formation. Atomization energy is 150. First ionization energy is plus 736. Second 1450. With this step, I'm forming 1 mole of oxygen atoms. That should be the atomization energy, and luckily that is what they give me, so stick 248 on that arrow. First electron affinity is -142, second is +844, that's for oxygen, and that's all my numbers put on my cycle. Following the arrows around to get the last enthalpy should come out as being +3888 kilojoules per mole. So there we've looked at the slightly harder examples of Born-Haber cycles. So if you look back to the past paper document I sent you or in the Google Classroom, you should be able now to do up to question 9.